Welcome to this explainer. Today, we're diving headfirst into the high-stakes world of systems engineering. We're going to uncover exactly how incredibly complex, large-scale projects, the kind that literally change the course of human history, are orchestrated so they don't just collapse under their own weight. If you've ever wondered how on earth thousands of people manage to build something massive without the whole shebang falling apart, well, you're definitely in the right place.
Let's kick things off with a pretty visceral reality check. Think about the Apollo program. The goal, as we all know, was to land a human on the moon and return them safely to Earth. I mean, it sounds straightforward enough when you summarize it in just one sentence, right? But the reality of actually pulling off that mission, absolute coordination nightmare. You see, the Apollo spacecraft wasn't just a single machine. It was a massive system of systems. We're talking the command module, the service module, the lunar module, the rocket, plus all the ground control infrastructure. Put it all together, and this system contained a staggering 5.6 million parts. And get this, those parts were developed and coordinated by an army of 20,000 contractors and 400,000 personnel. Every single one of those 5.6 million parts had to function flawlessly, together. No pressure, right?
And that staggering complexity brings us to a core truth we really need to keep in mind. Complexity kills success, unless it's managed properly. That right there is exactly why systems engineering exists. It isn't just some dry technical discipline. It is a strategic framework designed to mitigate terrifying risks. Think about when the Apollo 13 oxygen tank exploded. It was a profound, deeply ingrained understanding of the entire system that allowed those engineers on the ground to improvise, manage the crazy life support and power constraints, and actually get that crew home safely. So to tame this kind of chaos and bring some real discipline to innovation, we gotta figure out what systems engineering actually is at its core. Section 1. What is systems engineering? Well, if we look at how NASA defines it, systems engineering is a systematic interdisciplinary approach that spans the entire life cycle of a system. It doesn't just zoom in on the build phase. No, it looks at everything, from the initial design and realization to the technical management, daily operations, and even the eventual retirement of the system. It's there to make absolutely sure that all the interacting elements, the hardware, the software, the facilities, the personnel, and the procedures actually do what they're supposed to do and fulfill the overall mission need. Basically, it forces you to view the system as one giant holistic entity rather than just a bunch of isolated parts floating around. Now, here's a super common point of confusion. What's the actual difference between a project manager and a systems engineer? Okay, think of the project manager as the conductor of an orchestra. They're laser-focused on the who, when, and how much. They manage the schedule, the budget, the resource allocation, basically keeping the orchestra playing on time. The systems engineer, on the other hand, they are the composer. They're the architect. They focus on the what, why, and how. They're the ones making sure the music being played is actually harmonious, technically sound, and, capable of meeting the end user's needs. So, one focuses on execution while the other focuses on technical coherence. Make sense? Section 2. Unpacking the SE engine. To act as this master composer we just talked about, NASA relies on a highly structured framework known as the SE engine. And this engine outlines exactly 17 common technical processes. Think of these 17 processes as the absolute backbone for managing complex project life cycles, right from day one all the way to the finish line. Now, these 17 processes aren't just some random list they threw together. They're carefully broken down into 3 really crucial buckets. First up, we have the top-down system design processes, which is where you define the architecture. Second, we've got the bottom-up product realization processes. That's where we actually build, integrate, and verify the physical system itself. And then, wrapping all of this together in a nice bow, we have to cross-cutting technical management processes. This includes things like risk management and technical planning that basically keep the whole show on track. Section 3. The system design process. Let's zoom in on that first bucket for a second, system design. This is where the absolute most critical early decisions are made. This top-down approach follows a very specific, rhythmic 4-step process. Step 1 is stakeholder expectation definition, where you're just figuring out what everyone actually needs. Then, step 2 is technical requirements definition. That's where you translate those broad needs into clear, verifiable requirements. Moving on to step 3, we have logical decomposition. Sounds fancy, but it just means breaking the architecture down logically into functions and interfaces. And finally, step 4, design solution definition, which is where you take that logical architecture and translate it into a real
physical design solution with specific hardware and software.
Section 4. Stakeholders and Hidden Voices.
Okay, so step 1 of that design process, defining stakeholders, actually holds a pretty surprising twist. Ask yourself this. When we hear the word stakeholder, who usually pops into your head? For most of us, it's the client paying the bills, the end user who's going to operate the thing, or maybe some external regulators, right? But here's the catch. Omitting the engineering team from this initial stakeholder group, that is a massive recipe for disaster. The absolutely crucial point here is that the builders themselves must have an early technical voice. Why? Because they're the folks down in the trenches who have to actually navigate the technical constraints and balance all those really tough trade-offs. If a requirement is physically impossible or just totally unachievable, it's the engineering team that's going to spot those system unknowns early on. By bringing them to the table as key stakeholders right from the jump, you prevent scope creep and you stop completely avoidable, costly rework before it even begins. Honestly, leaving them out is like trying to design a massive cruise ship without ever talking to the people who actually have to weld the steel together. It just doesn't make sense.
Section 5. The True Cost of Design.
So bringing that engineering team to the table early ties directly into a pretty sobering reality about project costs. Picture this. You've just wrapped up the early design and concept phases of your project. At this point, if you look at your budget, you've typically only spent a mere 15% of your allocated funds. Looking at the numbers, it feels like you've got a ton of runway left, right?
Well, however, and this is where it gets absolutely critical, because you have already locked in your architecture, defined your subsystems, and made your core technology choices. That 15% spend has already committed up to 75% of your final total project costs. Let that sink in. You haven't actually spent the money yet, sure, but your early design decisions dictate that you are absolutely going to have to spend it on specific manufacturing, testing, and operational maintenance down the line.
This whole cost commitment reality proves exactly why systems engineering is so incredibly vital. It forces us to take a step back and ask a really hard question. Are our early decisions thoughtfully managing complexity up front, setting us up for success? Or are we just blindly locking in a disastrous, massively costly failure for the future? Seriously, take a look around at some of the failing mega projects making headlines today and ask yourself, did they actually fail at the end? Or were they already totally doomed at that 15% mark?